All right. Well, happy week 7. So week 7, it feels like, I remember quarter system. Week 7 was always kind of this turning point, and I don't know, it just felt like you got kicked up into a higher gear, and I don't know, it's crunch time. Maybe, I don't know, maybe that was just my experience. And it's Wednesday, so I hope you enjoyed your day off, and I hope the homework's coming along okay. And I just posted homework 5, so that's there. So you will see, floating point stuff, and we're introducing some numeric methods, and yeah, no rest for the weary, huh? Okay, but again, and I saw some good discussion on Campus Wire, and it's kind of one of those things where if you got like 90% of it working, all right, just it's okay. You can turn it in. You'll get 90% of the points, and that's all right. Life goes on, right? So you don't have to try to get 100% or perfection on everything, right? You got to balance like sleep along with everything else, and I want you guys to be okay with those choices. Others of you have it working 100%, and that's great, and I'm happy for you. All right, we are going to take a look at root finding methods, and so we're progressing into some numeric methods. And so again, thematically, the course can be divided into kind of 2 halves. First half being very heavy on programming ideas, programming concepts. We saw a bunch of stuff there. And then the second half focuses a lot on kind of computational aspects in statistics. And so, we started off by just talking about floating point numbers, just because it's important to understand that your computer doesn't deal with real numbers, right? A lot of times we use type double, and we kind of treat them as if they were real numbers, but they certainly are not real numbers. And there's some side effects where you lose a lot of precision. And basically at any kind of level, there's, your computer can provide around 16 places of, 16 significant digits of precision. And that's at its very best, okay, at its very best. And most places, you're going to have a lot kind of less precision. But that's okay. We use the computer, and in most of these cases, it's good enough, right? And so, we're going to take a look at some numeric methods. Today's root finding. But in general, numeric methods are techniques or algorithms that provide approximate solutions to mathematical problems. Okay, numeric methods take advantage of what the computer is good at, which is doing quick computations and doing computations and doing them quickly. In general, computers aren't good at like thinking about math and having concepts of theoretic math. I have to kind of qualify that because some software has been written that now performs really well and is able to do kind of this symbolic manipulation, right? Like there's Wolfram Alpha, a website where you can plug in equations and it's able to solve these things, right? That is a testament to some very ingenious software being written, okay? But at the core level, like what is the CPU really good at? It's good at multiplying stuff. It's good at doing this very quickly, right? So, you think of like GPUs doing mining for cryptocurrency and stuff. It's just basically like, here's a whole bunch of like things doing a whole bunch of calculations really, really fast. And that's what numeric methods kind of take advantage of. So when we want to use numeric methods, we want to use these when you have some kind of mathematical problem that do not have an exact or analytic solution using algebra or calculus. So there's a lot of problems where, you don't have closed form solutions and stuff. Or even if there is some kind of closed form solution that exists in theory, perhaps it could be very difficult, some kind of intractable solution that it would take like a really long time to figure out how to compute it, okay? And so these numeric methods take advantage of just what the computer is good at, which is, follow instructions, do them very quickly, do a bunch of calculations that, are approximately good, okay? So again, anytime you ask the computer to multiply some numbers or subtract some numbers, you're going to get not the exact thing, right? You do 0.1 plus 0.2, you're not going to get the exact answer of 0.3, you're going to get something close enough, all right? And we have to kind of accept that, right? So here's an example where we're basically doing a numeric method. So I think a lot of you either have taken 100B, Stats 100B, or are taking Stats 100B, or I guess, what's the equivalent, Math 170S, okay? All right, and I think somewhere along the way you learned that the normal distribution, right, the PDF, or when you take the cumulative distribution function of the normal, right, there's no closed form solution, right? The CDF of the normal we don't have a closed form solution. So, when you took intro stats, what did you use for your CDF of the normal distribution? What did you use? You used a table, right? You used a Z table, and you just said, okay, it goes from like negative 3.49 to and incremented in hundredths, right? And today, you have R, and you have this function P norm, and you put in numbers, and it gives out pretty good numbers, okay? But what the computer is doing is it's not doing some closed form solution. There's actually this, R uses this algorithm 715, SpecFun, and it's written in Fortran of all languages, okay? And this is basically a numeric approximation. It's accurate to around 15 decimal places. And we say, hey, that's about as accurate as computers can do anyway, so that's good enough for us, okay? But is it truly the mathematical solution to this? No, it's not. But it's accurate to about 15, 16 decimal places, and we say, oh, well, the computer isn't even capable of showing more than 15 or 16 decimal places, so there's no sense in bothering. And so that's what we're doing now. We're not going to cover this particular thing in this class. Later on in one of your courses, 102C, if you take that, you'll learn about like inverse CDF method and for generating random numbers and stuff like that. So that comes later. But anyway, that's an example of a numeric method. And we say, yeah, but for all intents and purposes on the computer, using P norm is good enough to give us the CDF of the normal distribution. All right, today we will look at root finding methods. So what are root finding methods? Root finding methods is where we find the roots of a function, basically where the function is equal to 0, right? So if you have some continuous function f, we're going to say this function maps from real numbers to real numbers. So, your input is there's a set of real numbers, and then the range is, I guess not necessarily all real numbers, but you can put some kind of, you put a real number in and it spits a real number out, versus other functions where it might spit out a complex value, or maybe a higher dimensional thing. Okay, and the root is where f of x is equal to 0. So visually, if you are able to even plot the function, right? And some functions we can't really even plot, but this would just basically be where the function crosses the x-axis. And, a lot of kind of problems can be expressed in terms of finding a root. And so, there's lots of applications. So today we're looking at root finding. And in either the next lecture or the one following, we're going to basically say, all right, how do we find optimization, right? Optimization is finding a local min or local max. And that can be basically turned into a root finding problem by saying, find where the derivative is equal to 0, okay? So this serves as a good starting point. Okay, here's an example of finding roots, not using a numeric method, just using with an analytic solution, right? So, I don't know, you learned this in what, 8th grade, 7th grade? I don't know, when did you take algebra, right? You got a quadratic polynomial. You have the quadratic formula, negative b plus or minus square root, this and that. And there you go, roots of your quadratic polynomial. And that's great. That works perfectly. And as a rule of thumb, or not even rule of thumb, this should be the rule. If there is an analytic solution and it's easy, use the analytic solution that's easy, okay? Don't go with a numeric method, okay? The only time you really want to use a numeric method is if that analytic solution is difficult or not possible, okay? You can kind of think of this as like there's a door. You need to get to the other side of the door. If you got a key, use the key, all right? A numeric method is like taking a hammer and trying to smash down the door, right? It's this very kind of brute force method that says, all right, we're going to throw the power of the computer to try to get our solution. And you know, and at best you're going to get an approximate solution anyway. So it's not great, but sometimes this is what we're left with. Now that said, all of the examples I'm going to do today are like ones where a numeric method or analytic solution would have been way easier, okay? Like we could find all of the answers. In all the examples I'm going to do today, analytic solutions exist. And then also in your homework, all the examples, maybe not all the examples, but a lot of the examples will be like, okay, I could have just solved this analytically. But just kind of for illustration and just to kind of get through it, you'll use the numeric methods, okay? References that we'll be looking at, this is the textbook. You've already seen some stuff from this textbook, and it kind of goes on into, I guess, the scientific programming aspect and the simulation stuff, and then some other notes written on this. Okay, let me go ahead and give you your first view quiz answer for today, which, where did I put it? Okay, it is the letter C. C as cat. C as in cat is your first view quiz answer. C as in cat. All right, first method is called fixed point iteration. So let's talk about what a fixed point is. And so fixed point iteration will help us find fixed points, not roots, but we'll adapt it to find roots. Okay, so let's say we have some function g. G is a continuous function. A fixed point of g is where g of x is equal to x. All right, so graphically, think of the line y equal to x, so diagonal line running through the origin, y equal to x. Where does your function g cross that line, y equal to x? Where it crosses will be fixed points, okay? And because g of x equals x, one property is that if you take g of x, you get x. And if you take g of x, you get x. And if you take g of x, and so on and so forth, you keep getting x back, right? So you can kind of, once you're at a fixed point, you can keep applying the fixed point to this thing, and you keep getting itself back. Now, fixed point iteration depends kind of on this concept of an attractive fixed point, right? So some fixed points are what we call attractive fixed points, okay? And so if we have some fixed point A and it is attractive, okay, if we're able to start at some arbitrary value x kind of close to A, and this is just a vague term, close enough to A, that if I start off at x and I take g of x, and then I take g of that result, and then g of that result, so g of x, okay? And I keep doing this. If it converges to A, we would say A is an attractive fixed point of the function g of x. So a little bit more formally, we're going to say g super n of x, okay, denotes the iterated function of applying g n times. And we're going to say for all x, then this quantity converges to A as n goes to infinity, okay? So here's an example of an attractive fixed point, the square root function, all right? I don't know, did you ever play around with a square root function in grade school when you first got your calculator, right? You plugged in like, a big number, and you say, okay, what's the square root of this thing? All right, 10 million, what's the square root of that? 100, what's the square root of that? 10, what's the square root of that? 3.162, and what's the square root of that? 1.778, what's the square root of that? 1.333. And you keep taking the square root, and what happens? It gets closer and closer and closer to 1, and after a whole bunch of these things, I'm at 1.000, and we can just imagine as I keep going, I'm going to eventually get to the value 1, right? And you can plug in any kind of arbitrarily big number, and you say, I'm going to keep taking the square root, and even after, I don't know how many buttons I clicked, but after just a few, I'm at 1.03, and as I take more and more square roots, we can see this is going to converge to 1, okay? Going in the opposite direction, I can start off at some really small value close to 0, and I take the square root, and I get 0.34, square root of that is 0.58, square root of that is 0.76, square root of that is 0.87, 0.93, 0.966, 0.983, 0.99, okay, and eventually I'm at like 0.9999 something, right? So the square root function is has an attractive fixed point at x equal to 1, right? You start at any kind of value, you keep taking the square root, eventually that thing is going to converge to the value 1. So that's the idea of an attractive fixed point. A lot of functions, not all, but a lot of functions do have attractive fixed points. And so if a function does have an attractive fixed point, how do you find the fixed point? Well, you just start off at some value, and then you just keep running the function, okay? Just like we start at some value. If somebody said, hey, what's an attractive fixed point of square root of x? Well, you just say, well, start somewhere, and just taking the square root, and if it converges somewhere, that's going to be your fixed point, right? And so assuming if we have an attractive fixed point of some function, how do we find that thing? We just start off at some value, we keep applying the function, and we just do this over and over and over again. So basically, as far as in notation, that means x at the next iteration, x at time n plus 1, is just g of your current value, x at time n, okay? And we just repeat, okay? The next value, x at time n plus 1, is g applied to your current value. And then you just keep going, okay? And so we just keep applying the function over and over and over again, and if the function does have an attractive fixed point, this will eventually converge to that thing. Now, to avoid iterating forever, right? And so this is where we have to understand the limitations of numeric methods, is that you're never going to get to that exact value, right? Like I can keep taking the square root of this thing, and I'm never actually going to get to 1, right? So if I start off with some value and I keep taking the square root, I'm never actually going to get to 1, right? I'm going to get more and more close to 1, but like I'll never actually get to 1, right? And I don't even know how the computer is showing me this many decimal points of precision. Okay, so I don't know what it's doing. There's something super scientific happening inside the calculator app on Windows there. But anyway, we just say, all right, when the difference between our current value and the previous iteration is less than some tolerance, right? Like 10 to the negative 6 or 10 to the negative 7, some value, we're going to say, all right, that's good enough. Okay, that's good enough, and we're going to stop, right? So numeric methods mean you have to be okay with good enough answers. Okay? You'll never get exact answers, right? We're always going for approximations, and we're saying, all right, that's good enough. When the difference between this and this is less than some tolerance, then that's good enough, right? And so we talked about floating point numbers, so you understand that this tolerance, depending on what size you are, like the smallest measurable differences, can never be more than like to the negative 52, versus the thing, right? And obviously probably something much less than that, or much more than that. Okay, so here's a little illustration. I don't know what happened to this graph here, but this is the square root function, okay? And I'm going to plug in 10, all right? And so what is the what is the square root function at 10? The square root function at 10 is right here, which is around 3.16, okay? And we're going to say, all right, where does 3.16, okay, this line over here is y equal to x, all right? So 3.16 is right here. So we started off at 10. Square root of 10 is 3.16, All right, so this line representing y equal to x, we're going to say, okay, well now we're going to plug in x equal to 3.16. Okay, when I plug in x equal to 3.16, what's the square root of that? The square root of that is 1.778, which is right here, okay, this green line. And now that's going to be the next value I plug in for x. So I'm going to come down over here, I'm going to plug in x is equal to 1.778, and I say, all right, what's the square root of that? That's around 1.33, and so that comes over here. And then we plug in 1.33. What's the square root of that? 1.15. And then I keep going and going and going. And you can see, all right, this is going to eventually converge to something close to 1. And so after around 15 iterations, I'm at 1.00007. Okay? And that's fixed point iteration for the square root of x. So that's kind of an illustration of, how we find fixed points. We just, assuming it has an attractive fixed point, keep plugging in the value, keep plugging that result in back into the function. Okay, our goal though is to find roots. So how do we use this to find roots? Well, so we're going to say, let's say we have a function f and we want to find the roots of f. Okay, what we have to do is we just have to find a similar function g, okay, so that when g of x equals x, f of x is equal to 0. Okay, so we find a function g of x related to f of x, so that when g of x equals x, when we find the fixed point of g, we have a root for f. So for example, one possibility is I could define g of x as x minus f of x. Okay, and if I do this, then f of x is equal to 0 when g of x equals x, right? So when this is true, when g of x equals x, then f of x has to be 0 if we define g of x like this, okay? And so I can find if I find the fixed points of g of x, then those will be the same locations where we have roots of f. Okay. Now often there's going to be lots of ways to figure out. There's going to be lots of g of x functions. Okay, lots of functions g of x equal to x, so that f of x equals 0, and some will work and some won't. Right. The idea and the hope is that g of x will have attractive fixed points, and you might have functions g of x where g of x equals x and f of x equals 0, but g of x doesn't have attractive fixed points. So here's an example. Let's say, and this comes just from the textbook. Let's say this is the function, and we want to find roots of this function. So f of x is log of x minus e to the negative x. So one thing about log, anytime I write log here, it's natural log. Okay, it's always natural log. If I want common log, I'm going to write log 10 of x. Okay, so anytime you just see log, that's going to be natural log. And that's the same on R. You type in log, that's going to be natural log. Okay, so we want to find a solution, find the root of this function. Log of x minus e to the negative x is equal to 0. Okay, so what is some function g of x, so that when g of x equals x, f of x equals 0? Well, one way is I can kind of take this and say, hey, you know what? It looks like it's pretty easy to solve for x. So I'm going to do log of x minus e to the negative x equal to 0. This is what we want to do. I'm going to move e to the x to this side, do e, raise e to this power. So I'm going to have e to the e of negative x. And if we say g is equal to this thing, when g of x is equal to x, that's got to be where f of x equals 0. Okay, and so we'll do this. So does this have? We'll try to find fixed points of this function, e to the negative x, and when g of x equals x, then that's going to be where f of x equals 0. All right, so this is the code that will do fixed point iteration. Okay, we're going to start off with our function. Our function is e to the e of negative x, so I've got exp of negative x. Okay, I'm going to start off at some arbitrary point. I'm going to just throw in x, or my old value of x is 10. My new value is going to be g of x old. I'm going to start off with 0 iterations. I'm going to just pick an arbitrary value of 10 to the negative 8 for my tolerance. And then I just run a while loop. Okay? And we're going to say while this difference is greater than the tolerance. So basically keep going until the difference between the new value and the previous value is less than the tolerance. When that difference is less than the tolerance, and then we'll stop. What we're going to do, take the my current value, x new, set that to my old value, and then g of the old value becomes my new value, right? And so we're doing this kind of step by step. I'm going to increment my iterations, and we'll just let this run, okay? Now, sometimes you're in a situation where it doesn't converge, all right? And so to kind of prevent it from running forever, you might want to have a secondary stepping criterion that just says, hey, if iterations goes over 1,000 or something, then stop the loop, okay? So anyway, I run this, and we arrive at a solution. I say, all right, what's my solution? My approximate root is 1.3098, and we say, okay, does that give me a good answer? We plug in 1.3098 into log of x minus e to the negative x. So log of this value minus e to this value. Yeah, I get 9.7 times 10 to the negative 10. So something on the order of 10 to the negative 10. So then I say, okay, that's pretty good. That's pretty good. That's close enough to 0. And that's going to be our approximate answer, right? And it took us 19 iterations to get to that answer. And that's fixed point iteration, okay? Here's a little bit of math that just says, yep, if the fixed point iteration method converges, then we can show that it converges to a fixed point. And I'm kind of skipping over some of these math little proofy slides here, just so we can cover a little bit more ground. You can review this on your own time. But does fixed point iteration always converge? And the answer is no, it doesn't. Okay. For fixed point iteration to converge, we depend on the existence of an attractive fixed point, and not all functions have attractive fixed points. One kind of sufficient condition is that if you can take the derivative at the fixed point, g prime of x, if the derivative, absolute value of the derivative is less than 1, then that fixed point is going to be attractive. And if the derivative at f of x, or at g of that fixed point is greater than 1, it's a repelling fixed point. All right, so here's an example where we have a repelling or diverging case. So we have the same function, log of x equal to e to the negative x, and we could say, oh, you know what? Let me just add x to both sides, okay? And then so if I say g of x is equal to this, log of x minus e to the negative x plus x, and I say, okay, when g of x equals x, that's got to be when f of x equals 0. That's true, okay? The problem is that this function g of x does not have an attractive fixed point, okay? So this is true. When g of x equals x, then f of x will equal 0. But this function doesn't have an attractive fixed point, so when I run the algorithm, and so it's the exact same code. I just changed what my g of x is. G of x is this, basically f of x plus x. If I plug that in, okay, and now I have this condition that says if the iterations goes over 1,000, then break. So we stop the loop so we don't run forever. Okay. If I do that, we don't find the root, right? The solution was like 1.3098, and here we end up at x being 7,830, nowhere close to the answer. We plug that in, we're nowhere close to 0, and we've done 1,001 iterations, and that's why it stopped. So that's what we have there. Okay. All right. Let me go ahead and give you your second view quiz answer. Second view quiz answer is the letter B. B as in bear. B as in bear. And let's talk about Newton-Raphson method. Okay. So fixed point iteration is considered to be relatively slow, and Newton-Raphson method is much faster, okay? And the idea behind Newton-Raphson method is that we're going to use the tangent line, okay? And the tangent line at some point is the best linear approximation to the function at that point, okay? And so let's say we are looking for some root a, okay? We have some function f and we want to find the root a. And we're going to, for Newton-Raphson method to work, f has to be differentiable and there has to be a continuous derivative, okay? So we're going to say we start off at some initial guess, x0, and the linear approximation to the function f around x0 is the equation of this tangent line, f at x0 plus f prime at x0 times x minus x0, right? And I don't know if you remember Taylor expansions from your good old days in calculus. You know, we can approximate, or we can, you can get the equivalent of any function by just kind of expanding this forever, right? And if you just throw away some high order terms, then you get an approximation to some degree. And basically, we're just taking the first two terms, right? And so that's a linear approximation of some function. So that's what we're doing here, okay? And so the way we're going to do is we say, all right, let's start off at some, we have some function f and we have some kind of tangent thing, okay? And we're going to follow that tangent line down to where that tangent line crosses the x-axis. And then we're going to use that location as the location for our next iteration. And so, again, I'm using an example where like we could have found the analytic solution very easily, but we're going to do Newton-Raphson method. Okay, so my function is x squared minus 3. Okay, so we know the solution is going to be square root of 3. Okay, but we're going to start off at x0 equal to 10. I plug this in, and so here x0 is 10. I plug this in, we're going to get 97 here. And we say, all right, what's the tangent line at this location? So we trace the tangent line. We follow the tangent line until it crosses the x-axis. And we say, all right, where does this cross the x-axis? It crosses the x-axis at 5.15. I plug that in, I get 20-something, okay? And there's a new tangent line here. And we follow that tangent line. And we end up over here, and that's 2.866. And we follow this, and we come down to here, and we get x squared, 1.956, and we follow that, and we can see, after 1, 2, 3, we're getting pretty close to our solution, right over here. Okay. All right. So how do we figure out where this line crosses the x-axis? How do we figure out where this tangent line crosses the x-axis? And I said it crossed at 5.15. How do we figure that out? Okay, so we look at kind of this crude drawing, and they teach slope is equal to rise over run, I think, right? Those are the terms we use back in 8th grade or whatever. Rise over run. So we say, all right, let's look at this triangle here. Okay, this triangle starting at x0 equal to 10. Okay, so the function is 97. Okay, the value of the function, x squared minus 3 is 97. That's going to be the length of this side, so that's going to be my rise, 97. And so we say slope is equal to rise over run, and we want to know, okay, what is the length of this run? Okay, well, just with a little bit of algebra, we're going to say the length of the run is going to be the rise divided by the slope. Okay, and what's the slope? Well, the slope is f prime at x0. Okay. So, this is very solution. F prime, very simple. F prime is 2x. So I plug in 10, and so my slope is going to be 20. Okay, so the slope of this line is 20. And so my run is going to be 97 divided by 20. I get the length of this thing is 4.85. So I know it's going to cross the x-axis at 5.15, 10 minus 4.85. All right, so x at time 1 is going to be my current value, x0, basically 10, minus the height of the function f of x at 0 divided by the slope at x0, f of x0 divided by f prime of x0, and that's what we get. Okay. Okay. All right. And so in general, x at time n plus 1 is going to be x at time n minus f of x n divided by f prime at xn, and that's going to be Newton-Raphson method. All right, so so this is our algorithm. X at time n plus 1 is our current value, f of x divided by f prime of x. And we just stop when f at time xn is close enough to 0, meaning it's less than or equal to some arbitrary value epsilon, our tolerance level, okay? And we're going to say, okay, well, that's close enough to a root, right? So again, we're always going for approximate answers. If you need an exact answer, a numeric method is not the way to go. You will not get it. You'll never get an exact answer. Approximate answers. All right, so let's go ahead and try this out. Here's the same function, log of x minus e to the negative x. And so we got to figure out the slope. All right, so we need the derivative. Okay, derivative is derivative log of x is 1 over x. Derivative e to the negative x is e to the negative x. Chain rule, so we multiply by negative 1, and we get 1 over x plus e to the negative x. That's f prime. So if it's been a while since you've taken derivatives, brush off, dust off those derivative skills, right? So I think it's reasonable if I were to give you a problem where you have to figure out the derivative of like your trig functions and stuff, right? Derivative of sine and cosine and tangent and those kinds of things. I won't do hyperbolic trig functions though. That's sort of like, oh gosh. But anyway, so f is going to be log of x minus e to the negative x. F prime is going to be 1 over x plus e to the negative x, okay? And then this is the Newton-Raphson algorithm. It's just like, what, 3 lines here even, okay? So we start off at some value, okay? Arbitrary value x equal to 2. I'm going to start off at 0 iterations. My tolerance will be 1 times 10 to the negative 8. And while this difference, or while the absolute value of f of x is greater than my tolerance, we'll keep running. And we'll say the next value is going to be x minus f of x divided by f prime of x. That's going to be x. Increment my iterations, and boom, that's Newton-Raphson method. Okay, and look at that. We got 1.3098. So sure enough, that's our approximate root. I plug that in. Sure enough, that value is pretty close to 0. Okay, 10 to the negative 9. Okay, and it only took us 4 iterations, right? So fixed point iteration took us around 19 iterations. Newton-Raphson only took us 4 iterations. Now, you're not going to detect the time between 19 iterations on your computer and 4 iterations. This is like a very quick kind of thing that both of them take, a split second. But Newton-Raphson in general, it converges much faster, okay? All right, so here's a little bit of math proofy stuff that just says, yep, if it converges, okay, if it converges, then it's going to converge to a root, okay? It's going to converge to a root. Now, one of the things is that, the derivative of a, f prime of a, this can't be infinite, okay? So like, some functions like tangent of x, there's locations where the derivative is infinite, so that's not going to work, okay? Does it always converge? And the answer is no. Newton-Raphson method does not always converge, and this is gonna be a common theme throughout like the 102 series. Is that we'll have these numeric methods like for optimization and things like that we're like, okay, we want this to work, and a lot of times it works, but a lot of times it like breaks. Like it doesn't always converge, doesn't always find the solution. So we say if f is well behaved meaning the derivative at a isn't equal to 0 and the second derivative is finite and continuous, then if that's the case and your initial value is close enough to a, then it will converge quickly, okay? And Newton-Raphson method converges quadratically, which, don't worry about what that means, but just basically it converges very quickly, all right? But it's not guaranteed to converge. All right, and then sometimes even if it does converge, it might not converge quickly after all. Okay, it's like all of these like caveats and conditions, right? So here's some examples where the Newton-Raphson method will fail. If you have a function where the derivative is equal to 0 and you hit that location during your iterations, then the tangent line ends up being flat, and it won't cross the x-axis, right? So you're not going to have a next iteration. So then it fails, okay? And even if it isn't flat, okay, if your slope ends up being close to 0, like 0.01, so you have this very slight angle, and so if you evaluate the thing and you follow this tangent line to where it crosses the x-axis, it might end up super far away, right? If you have this very slight slope to it, okay? So you can end up far away, and that could end up causing problems. Now, we don't want that saying that f prime can't be 0 for any of these n's is different from saying f prime can't be 0 at all, okay? So you can have, like, if we said your function can never have a derivative equal to 0, then basically you can't have any function that is going to have a local min or local max, right? So we're not saying that. We're just saying as you're evaluating your iterations, you can't hit a location where the derivative is equal to 0, okay? So if you run your iterations and you hit a location where the derivative is equal to 0, you might be able to solve it just by changing your starting location, right? So if you just change your starting location and you end up where, and you don't hit that location where the derivative is equal to 0, then you're in good shape, okay? So it's fine if the function does have a derivative equal to 0 somewhere along the point. You just can't hit that location during the course of your iterations that you're running. Convergence can depend on the initial guess, and so if the starting value is too far, you might end up somewhere else, or you might not converge. Sometimes you end up in these locations that oscillate back and forth. If your second derivative is infinite or undefined, it can cause non-divergence, and even in like it might converge, but it might converge slower. All right, so here's a link that illustrates Newton-Raphson method. All right, so this one is like basically the example we're looking at, something very similar, x squared minus 4, I have x squared minus 3. So basically, they started off at 10, and then this behaves nicely, so you follow this and it goes, all right, there we go. It converges something around 2, okay? Now here's a function that the root is over here, okay? Here's the root, but there's a spot where we get kind of this flat zone, and so you can see the algorithm kind of struggle to kind of get out of this thing, right? So it ends up over here, and it kind of oscillates back and forth, and it kind of gets trapped here, and eventually it ends up over here, and then it's able to find the root, okay? But there's kind of this this period where it gets kind of trapped in this rut, where there's no root, but because the slope is negative on one side and positive on the other side, it kind of goes back and forth, and it has a bit of trouble. So stuff like that can happen here. There's more examples of some of these kind of issues where we run into some problems with Newton-Raphson. Okay, but that's Newton-Raphson method. All right, let me go ahead and give you your last view quiz answer. Last view quiz answer is the letter A. A as in apple. A as in apple. Okay, so we'll cover secant method. I've got a few more slides on bisection, and we'll just look at them on Friday. Secant method is like Newton-Raphson method, except we don't require that you need to figure out the derivative. So one of the drawbacks with Newton-Raphson method is you got to know the derivative of your function, and you might be in a situation where you're like, I don't know how to figure out the derivative here, okay? All of our examples have been very simple, right? Your derivative was 2x. But you might be in some situation where you don't know the derivative, you're not quite sure how to figure out the derivative. So the secant method says, you know what? Don't bother with figuring out the derivative. Instead, figure out a point, find another point, and just draw a straight line that connects those 2 points. Draw a secant line that connects those 2 points. And that's kind of close to a tangent line, and that's the secant method. So let me just show you the picture, all right? So rather than figuring out the tangent line right here, okay, so I have the same function, x squared minus 3. I start off at 10, and rather than drawing the tangent line at x0, 10, I say, you know what, here's another point, x1 equal to 8. And we evaluate the function, and I draw a straight line that connects the point here and the point here. And I say, all right, that's kind of close to a tangent line, not exactly, all right? And then we say, okay, we follow that until we hit the x-axis, and we hit right here, all right? And so that gives me this location, 4 point something, okay? And then I say, all right, so now I've got a point here, and then here's my previous point, 8, and so I draw a line that connects there. All right, and, you know, not really looking like a tangent line anymore, but it's fine, okay? We follow that down to the x-axis, and I say, okay, here's a new location, all right, and here's this thing, all right, and we're going to draw a line that connects this dot to this dot. We're going to draw a straight line here, and we follow this, right? And so it looks very similar to Newton-Raphson method, except instead of tangent lines, we're drawing secant lines. We're picking 2 points on the thing, we're connecting them with a straight line, and we trace it down, okay? So if you think about what is this, all right, how do we figure out where this is going to cross the x-axis, okay? So basically, we're going to draw like the little triangle, and we say, all right, what's this rise and what's this run, and you know, what's the slope and stuff, okay? Or we want to figure out the run, right? So we know the rise. The slope is going to basically be the change in y between these 2 points and the change in x between those 2 points, okay? So change in y is, so we have two starting locations, x at time 0 and x at time 1. So the change in y is f of x1 minus f of x0, and the change in x is x1 minus x0. So this is basically my slope, and using that, we can figure out where it's going to cross, okay? So the next value it crosses is going to be at 4.611. So we say, you know, we're at 8. I subtract off basically f at 8, which is 61, divided by the slope, okay? And that gives me 4.61. So in general, this is kind of the math to get there, but I'm going to just kind of skip through it. We're going to say the next iteration, x at time 2. So if we have x at time 0 and x at time 1, so again, you need kind of 2 starting points. At your next iteration, you have x at time 2. That's going to be kind of your current value, x at time 1, minus f of x at time 1, divided by the slope. Okay? And the slope is just, or, you know, multiplied by the inverse of the slope. The slope is the difference between f at x0 and f of x1, and your change in x, you know, x1 minus x0. Okay, so it's very similar to Newton-Raphson method. It's just rather than figuring out the slope by doing f prime, we're kind of approximating the slope by taking a difference between 2 locations in x and and their corresponding f of x locations. Okay, and so that's going to be secant method. And so you'll have a little bit of that to explore in the homework 5, which has just been posted. Okay, and so so you kind of follow this. This is the algorithm to do secant method, and this is gonna you keep running until f of x is less than some tolerance level epsilon, and that's fine. Okay. Secant method runs into the same kind of convergence issues that Newton-Raphson method runs into, because they're pretty much very, very similar. It's just you don't need to know the derivative there, okay? And so kind of the trade-off here is you no longer need to have an exact form for f prime, but you do need to have two initial starting points, x0 and x1. Okay, so we'll go ahead and end here for today. On Friday, we'll pick up and look at bisection method, another root finding method. But we'll go ahead and end here. We'll see you all on Friday. Have a great rest of your day.